Thank you for coming for this weekly seminar. I'm Chithrabhanu Perumangatt. I'm from Center for Quantum Technology, National University of Singapore. My topic is linear and compact entangled photon source designs for quantum communication. Center for Quantum Technology at Center for Quantum Technology, our group is primarily focused on quantum communication, that too satellite-based quantum communication. So one of the prerequisites for enabling such communication is quantum sources. And the quantum source, one of the prominent quantum source is entangled photon source. And we are trying to make it more compact, stable, and it ready for deploying in real life applications. So much things we have to consider for that. So much engineering and physics perspectives you have to consider for designing such systems. So I will be describing three major sources that we have developed. And before going to that, I will be giving a short introduction towards entangled photon source. Okay, so why polarized entangled photon source? You can have entanglement in different degrees of freedom. First of all, this is one of the best platform for testing fundamental principles and quantum protocols. One of the reasons being polarization is a simple system, and this is a easiest representation of a qubit because it's a two-level system. You have horizontal and vertical polarization, or left circular or right circular polarization, and this is the polarized entangled photons is this platform of polarized entangled photon has been used to demonstrate many of the initial quantum experiments such as teleportation, super dense coding, and quantum key distribution. So that's the main interest in getting better and better polarized entangled photons. Apart from the fundamental principles, you can use it for quantum communication. So the quantum communication, what we are working now, it's already being commercialized. Even in some banks are using quantum communication, quantum cryptography for their transactions. So this is, I want to make a difference. This is the first step of quantum communication. We are exchanging classical information through quantum channel. That means we want to exchange some keys so that our communication is secure. So these keys these keys are still classical, it's zeros and ones, but we are using the quantum channels. We are using the entangled photon source or even some single photon source for enabling a secure communication of this classical information. So entangled photon source obviously can be used for this quantum communication in this first scenario, and as well as there are other systems, weak coherent pulses also can be used. Coming to the next is second scenario is that exchanging quantum information through quantum channel. So this we don't have really intense requirement for this because quantum computers are still not operational at our day-to-day life. Once these quantum computers are operational, it will generate quantum information. It will generate qubits, and you have to transfer these qubits from one quantum computer to another quantum computer. So one of the best way to do this is using entangled photon source and teleporting this information from one place to another place. So this is the basic idea of quantum internet. For this as well, you have to use an entangled photon source, and polarization being the easiest degree of freedom because you can easily manipulate polarization compared to other degrees of freedom, and the detection is also very easy. You can use a polarizing beam splitters and polarizers and wave plates to convert from one state to another state. So that's why more likely we can use this polarized entangled photon source for all these purposes. That's why we are more towards this polarization and entangled photons. Now, we how to generate this entanglement. One of the famous method for generating entanglement is via spontaneous parametric down conversion, or it's called SPDC. So this is using the Chi2 nonlinearity of a particular crystal, and you can have a pump photon splitting into two signal and idler photons, and these are entangled in many degrees of freedom. I will come to that in a moment. And we have recently put an archive version of a review article. This is a review of different entangled photon pair source based on this three-wave mixing or spontaneous parametric down conversion. There are other methods. You can use spontaneous four-wave mixing. This is based on Chi3 nonlinearity, where two pump photons are excited and de-excite a signal and idler. Also, there are quantum dots, atomic transitions, but most mature and commercially used method is none other than SPDC. Okay, now entangled photons from SPDC. So what is basically entangled in the photons generated from a spontaneous parametric down conversion? The inherently entangled degrees of freedom are nothing but time energy, position momentum, orbital angular momentum. So these are inherently entangled. So you don't have to do anything to prepare such source. You have some prerequisites anyway. However, you can get this from any spontaneous parametric down converted process. However, to get this to measure this entanglement, you need more complicated setup. For example, you need for time energy, you need a interferometry based measurement. So you need interferometric alignment for that. For the position momentum, you cannot send it to greater distance, because you cannot, once you couple into a single mode fiber, the information is lost. Again, orbital angular momentum, you need complex spatial light modulators to measure this entanglement. On the other hand, you can have polarization entanglement. This is not directly generated from SPDC. You have to use, you have to force them to become entangled. And so such entangled states are polarization and time bin. I'm talking about polarization now. So I'll be explaining how we can force them to be entangled, and how we can make sure that this is really stable, and it can provide a good platform for quantum communication. So in these cases, you don't have to much worry about the source. You have to up to a certain point, but here we have to have a good engineering of the source, such that you have a good entangled photon source. But in this case, the measurement is very easy, because as I said, it's based on some beam splitters, polarizing beam splitters, and wave plates. Okay, so this is a general recipe for building a photon polarization entangled photon source. Now, I have given 4 steps. The first step is selection of 2 orthogonal photon pair states. So you can have 2 horizontal photons and 2 vertical photons. And this can be generated by different methods. I will be explaining that in a moment. And the second step is superposition. Third step is compensation. And the last is splitting of signal and idler photons. Okay, the first step, how do we generate this HHOVV photons? HH and VV being horizontal and vertical. These are photon pair states. So these pair states are generated as using spontaneous parametric down conversion. So you have a Chi2 nonlinear crystal, you have a high frequency pump splitting into 2 lower frequency photons, total photons. One is called signal and another one is called idler. Now, signal is conventionally you call signal as the higher frequency, and this is a lower frequency, but it can be degenerate as well. So these photons are called heralded single photons, because if you know the arrival time of this, you can expect that the other photons is will be arriving at the same time, because they are generated by the spontaneous decay of one photon. So it's generated very quickly. That means it shares same time during its birth. So that's why it's a heralded single photon source. Now there are many methods of doing this. So one, primarily you have to do a phase matching to achieve this process. Phase matching is nothing but you have to make sure that the pump and the daughter photons phase are adding up. So K is the K pump is the phase of the pump, which is 2 pi n by lambda within the crystal, and similarly for signal and idler. So critical phase matching, for example, we use beta barium borate crystals. So you can change the angle of the crystal such that these conditions is matched. This is because you have a birefringence. So because of the birefringence, you can change the refractive index of only one polarization and not the other. So because of that, you can tune this refractive index and make sure that this condition is matched. That's how we ensure that the phase matching is properly done. And another method is quasi phase matching. In this case, you can have type 1 and type 2 SPDC. So type 1 being you have a the pump is in one polarization and signal and idler are in orthogonal polarization. And type 2 is pump is in, suppose, horizontally polarized, signal is vertical, and idler is horizontally polarized. Now there is another type of phase matching called quasi phase matching. This is by periodically polling of your material. So with the periodic polling, you can have an extra component for your momentum, and because of that, you can have much more control over the phase matching, and you can have type 0 phase matching where pump, signal, and idler are copolarized. And here we change this refractive index by changing its temperature. Okay. Now the second is superposition. So superposition is nothing but making sure that your two orthogonal states, HH and VV, are indistinguishable. So how do you do this? One is using interferometry. So make sure that you interfere this and this amplitudes in a polarizing beam splitter, or even you can use a normal beam splitter, and you generate this HH plus VV state with a relative phase. Another method is geometry. Suppose I'm generating HH in first crystal and I'm generating VV in the second crystal. You can make sure that they are traveling like co-propagating, and use couple into a single mode fiber to avoid any kind of position distinguishability there. So that is one way to do that. And again, this is also kind of an interferometry, but you can use birefringence. You have horizontal and vertical components, and using a birefringence walk off, you can make sure that these two are co-propagating, and you can attain indistinguishability like that. Another method is using momentum selection. This is done generally by type 2 phase matching, where type 2 means the output state is H and V. That means if signal is H, the idler is V, and this is degenerate. So this is the H photons, and this is the V photons. When you choose these two momentum components, it is indistinguishable. So it is SV plus VS state. So these are the general method of making them indistinguishable. Okay, the next step is nothing but compensation. So compensation is very critical. In my talk, I will be coming to this more in detail, because if you don't compensate, you will end up with a state like this. So this will not be a pure state, because the relative phase between HH and VV, this will have a dependence on pump wavelength and SPDC wavelengths. So this is a major problem, because this will degrade the quality of your entangled state. Note that this SPDC is a multi-mode process, so the wavelength of this signal and idler are probably many nanometers wide. So this will end up in a can be ending up with a completely mixed state. If you have not taken care, it will end up in a mixed state. So you want to avoid this thing. So first step is to avoid the dependence of this phase on this SPDC wavelength. That means signal and idler wavelength. So this is called post compensation. So post compensation is nothing but removing the dependence of the relative phase on the SPDC wavelength. So after this post compensation, the phi, your relative phase, will become phi as a function of lambda p only. So here lambda s and lambda I is a signal and idler wavelength, and lambda p is a pump wavelength. So this is generally enough for getting a really good high quality or high fidelity state, because we generally use a narrow line width pump. So this dependence is really negligible. So this is enough for most of the cases. So consider this scenario. You have lambda 1 and lambda 2, and you have horizontal and vertical photons. It travels through some nonlinear crystals, and when it travels to some nonlinear crystals as a part of the source, it picks up different phases. So lambda 1 picks up phi 1, lambda 2 picks up phi 2. By compensation, we can make sure that these phases are matched after this. So use a BB, suppose this is a BBA crystal, and you generate this different, this is because of the chromatic birefringence of the crystal. So use another crystal which reverts this effect. Make sure that this phi 1 and phi 2 transfer to phi dash. You can use YVO4 crystals, and this you can choose the correct length of the YVO4 such that this phi dash is only a function of lambda p. It will not be a function of lambda s and lambda I. Okay, the second is pre-compensation. As I said, by post compensation, we are not removing the dependence on the pump wavelength. We are only removing the dependence of the phase over the SPDC wavelength. So for the pump wavelengths, we have to do pre-compensation. So that means the phi, which is a function of lambda p, should be phi, which is a constant. Now again, consider the same scenario. You have two pump photons. That means this generates an entangled photon source, photon state, and this generates another entangled photon state, and these are the crystals in between. And in this case, you have phi 1 as a relative phase, and in this case it's as a phi 2. Now if the pump has two polarization, this will not work if you have only single polarized pump. If you have two polarizations of the pump, what you can do is that you can delay one of these polarizations according to its wavelength, such that the final final phase is a constant. Again, using another YV4 crystals, you make sure that for this wavelength, it introduces this delay. For this wavelength, it introduces this delay such that your final phase is a constant. And once you have a constant phase, this can be removed using a wave plate, and you have your favorite Bell states. So that's how you have to do the temporal compensation. And the last part is splitting of photons. So you generate this entangled state, and you need to so you have signal and idler. A signal and idler, you have to split the signal and idler into two parts. So that's how you want to send it, to one to Alice, one to a Bob, for the quantum communication. So there are many methods. One of the method is dichroic mirror. So dichroic mirror is used when you are using a non-degenerate parametric down conversion. That means the signal and idler are of different wavelengths. So this is a really good method. It's a very compact, and it has good efficiency in general. And it's a very simple design. One of the drawback is that it has multiple reflections. So it has wavelength dependent reflection. So each wavelength will reflect in different layers. Because of that, it picks up different phase, and it can reduce the fidelity of your system. If you choose a wavelength range, very small wavelength range, this is not so prominent. But if you're working with a really broad SPDC spectrum, then this will reduce the fidelity. And of course, this cannot work for degenerate case. The second method is using WDM. This is a fiber-based method. This is called wavelength division multiplexing. And wavelength division multiplexing, you can split, again similar to this dichroic mirror, but this is using the resonance coupling in a waveguide. So this is it does not, good thing is that it does not introduce any wavelength dependent phase. So that's why it will not affect the fidelity. It is observed to be a bit less efficient than the dichroic mirror, and it will not work for degenerate case. And since there is a the fiber involved, you need to do polarization correction afterwards. The third is wedge mirror. So this was a favorite choice for a non-collinear phase matching. So non-collinear means the signal and idler are in different direction. But this we have done experiments such that this will work even using a collinear. It's because of the inherent momentum correlations. And this is good because it has no effect on fidelity. It has good efficiency, and it works for all degenerate and non-degenerate cases, and even non-collinear cases. The output contains both signal and idler wavelengths. So this is different. In this case, it's only one wavelength. This is idler, and this is signal. This is signal, and this is idler. Similarly here as well. But in this case, you have both wavelengths in both sides. This can be beneficial, and it can be a problem as well because it's not narrow, spectrally narrow. But it can be used in wavelength division multiplexing. I'll be coming about that point later. Only problem here is that it's a bit complex because you have to position this wedge mirror. So this is just a mirror coated here, and so here there is a coating, a metallic coating. So in this case, you have to position this mirror exactly at the center of this beam. And so for designing, it's a bit complex. Other than that, this is really efficient way of splitting signal and wave idler. Okay, that's it. And I will give a three sources which in the old literature. So this is one of the oldest source. This is based on type 2 phase matching. It's published in 1995. You have H cone and Y cone. Because of the walk off, it produces different cones. And if you select, as I mentioned previously, if you select these 2 points, two diametrically opposite points, you can generate the state HV plus BH. Another is cross crystal. So you use a pump of diagonal polarization, and you have crystal 1 which convert H to VV, and another will convert V to HH. This is type 1, and you choose two diametrically opposite points, and they are entangled. The fourth, this is not only one work, there are many variations of this. You can use a Sagnac interferometer, where you have a pump and daughter photons are oscillating. It's not oscillating, it's transmit. So the pump you have split into horizontal and vertical. Again, you have to use a diagonally polarized pump. The horizontal is down converted in this way, the vertical is converted to horizontal and down converted here, because it only allows type 1 or type 0, type 2 or type 0 phase matching. This is a half, you have to use a half wave plate which is special. It has to work as a half wave plate for both SPDC and pump photons. Similarly, you can have type 0 phase matching based design as well. So I have given a small introduction to the how to generate an entangled photon source. Now I will come to three sources that is designed in our lab, and these have common properties. They are linear. That means we don't need an we don't want to have an interferometer kind of design. And another is compact, and these are field deployable. That means it can be used, it has been used for quantum communication purposes. So the first source is parallel axis crystal entangled source, and this is based on PBO crystal. And to my knowledge, this is the brightest critically phase matched source. So this is the first source. The second source is a parallel path design. This can be the advantage of this design is that you can use a broadband pump laser and still attain a quality entangled photons. The third design is polarization entanglement from position correlation, and it has a more generic method, because it's not only based on SPDC. It can be applied to different systems, and it can make a really compact entangled photon source. So these are the three sources that I want to describe to you today. Okay, this is the first source. Okay, you have, in this case, we use a type 1 phase matching, and this is collinear type 1 phase matching. This is non-degenerate. We have two BBO crystals that undergoes spontaneous parameter down conversion. We use a vertically polarized pump, and the first crystal, this pumps walks down because of the spatial walk off, and it generates horizontally polarized photons. So at every point of its travel, it generates this horizontally polarized photons. So naturally, this will not walk off in the second crystal, but we have a halfway plate in between. So it flips this horizontally polarized photons into vertical. On the other hand, it does not do anything to the pump. So we have designed this halfway plate such that it does not change the polarization of the pump, but it flips the polarization of the SPDC wavelength. Now, this vertically polarized photons is extraordinary in this BBO. It walks down. It's again, the crystal axes are parallel, and the pump also walks down. It generates generates again horizontally polarized photon. And finally, you have horizontally and vertically polarized photons, and you use a YVO4 for compensating the phase. So this is a really good overlap compared to before some sources in the past where you have to use another crystals to compensate for the spatial overlap. In this case, it's inherently overlap, and because of that, you don't need to do any intense spatial filtering. Even if you use a multi-mode fiber, you can get a really good good quality entanglement. If you use a single mode fiber, the brightness is 65,000 counts per second per milliwatt, and the fidelity is close to unity. And this is published in Optic Express 2 years back. This we have used, this source we have used in a recent experiment. So this Spook is our satellite, which is still operating in low Earth orbit, and the Spooky has this parallel axis entangled photon source, and this is our this is our entangled photon source here. This has both the source and the detection. So you have two BBOs here, laser here, and YBO4 here, and it's split using a dichroic mirror and using two APDs. It's colors using two APDs, and this is published in Optica in this year. So that's why this is already proved to be versatile in a field deployable environment, in a harsh environment like in a satellite. Okay, coming to the next design. This is a parallel path design. So in this design, we have two paths. For now, let's assume, forget about these YVO4 crystals. You have a diagonally polarized pump. It splits into horizontal and vertical using a BBO crystal, and it travels parallelly, and the horizontal polarization is converted back to vertical, and it undergoes spontaneous parametric down conversion in a periodically poled KTP crystal. And this is type 0, that means vertical will go to vertical. And once, so this both have vertical polarization, and the lower path, the polarization of the photons generated in the lower path is flipped to horizontal, and the vertical is again walk back and combined here. In the second BBO, you have to choose the BBO lengths in such a way that this has good overlap. Now we employ a pre and post compensation here because you have diagonally polarized pump. In the previous case, we didn't have the diagonally polarized pump, so we cannot play with the phase of the pump. But here we can. That's why we can do pre compensation and post compensation. So we use a YVO for both of different length, such that the final state is compensated. I will show you the compensation later. So, but the really interesting thing is that you can use multi-mode lasers with low coherence length, even for this design, and you can get really good fidelity here. Okay, so this is a pump and SPDC spectra. As I mentioned, the pump is really broad, so it spans from 405 to 406, and the spectrum generated is also pretty broad. It's almost 100 nanometer broad. It's because each of them is phase matched with different conditions. Suppose this is phase matching in degenerate here at around 810, and this will degenerate. This will phase match in non-degenerate. So it fills up the spectrum like that. And the method of splitting this, we have used this momentum-based splitting, as I have mentioned previously. You have a wedge mirror it splits according to its momentum. That means if signal has this momentum, the idler will have another momentum, and you can couple into a single mode fiber. In this case, signal and idler does not mean lower and higher wavelength. It means just these two paths, that's all. So that means here both has the full spectrum here, and this is useful in wavelength division multiplexing. That means you can split the spectrum using another multiplexing method and improve your detection efficiencies, or you can do multi-channel communications using this. So the challenge is to have a really good fidelity over this really broad range, also with different pump wavelengths. So this laser is a really cheap laser. It's a $50 laser from Thorlab, and this is a free running laser. You can compare to the other the narrow line with laser. This is really cheap, and it can go to very high power. So these lasers, it does not have any feedback mechanism. Generally, if you have a volume holographic gating, that is how you generate this single frequency lasers. You cannot have higher powers, because at high powers the grating will be destroyed. But in this case, you can attain really high power. In commercially, you can get almost one watt of laser power. So you can, if you want to have a good entangled photon, quality entangled photons at high rates, you can use this kind of lasers. Okay, so this is what I was talking about, the compensation. So how do you know this is compensated? So what you do is you plot the phase difference. This is a phi as a function of lambda p and SPDC wavelength. So without compensation, you have this huge phase differences. You can see if you change the lambda p, the phase is changing drastically. Because of that, you will end up with a less entangled state, or a mixed state. But with pre-compensation, you can see the phase difference is almost negligible over a really long wavelength range of SPDC and pump. So this is directly seen if you measure the fidelity, or if you do the two polarization correlation of this entangled photon source. So this is generally this is the general method of assessing the quality of an entangled photon source by measuring the polarization correlation. So what you plot is a coincidence for different polarization angle, where one polarizer. So suppose in signal photons, I project this into horizontal, diagonal, vertical, and anti-diagonal photon, and I sweep the polarization of the idler photon, and you get this kind of curves. This is called bell curves, and you can get the Bell inequality from here. So by estimating estimating the visibility of this curve, you can estimate the fidelity of your source. Okay, so just some comparison. If you use, this design, you can use narrowband or broadband laser. So if you have a narrowband laser, you have a cost of $50, and at the same time, so broadband laser has a $50 price, and the narrowband is really costly. It's actually the costliest item to build an entangled photon source. So so this is really good if you can get a good entanglement using a broadband laser. The line width is several order of magnitude, because this can have really small line width, 0.08 picometer. This is 500.5 nanometer, or 500 picometer wide. The brightness is comparable. This is because at narrowband we are operating at degenerate. Degenerate has the highest brightness. In the broadband, some of them phase match degenerate, some of them will phase match non-degenerate. That's why the brightness is a bit lower, but still in the same order of magnitude. The visibility is also similar, because we have a good compensation, pre and post compensation. Because of that, you have a good visibility. This is not corrected for accidental coincidences, and this has a good, this indicates that our fidelity is higher than 99%. The maximum attainable counts means with the commercially available lasers how much you can get. That means this kind of lasers you can get off the shelf laser of 1 watt power, but this narrowband version, so far it's again about time, right? So as of now, the highest power we can get at this wavelength is 40 milliwatts. So the maximum attainable count rates is better if you use the broadband laser. Okay, I think that's it. Okay, the last source is a bit different. It's less towards the engineering, more towards the physics of the SPDC. We generate polarization and angle photons from position correlation, and this has a interesting application because it can convert your heralded single photon source. If you have a heralded single photon source, with this method you can convert this into a polarization and angle photon source. So it doesn't have to be a SPDC process, it can be a different process. And again, this has also a engineering application because it can make probably the smallest entangled photon source, and this is published in Physical Review A this year. Okay, so this was the initial experiment we have done. So what we have considered is that position correlation is inherent to spontaneous parametric down-converted photons. That means if photon 1 is generated at position x1, that means a signal is generated at x1, idler is also generated at x1. At the same case, if you generate at x2, both will have same position. They share same birth position. Now, in this case, suppose it's a type 0 parametric down conversion. It generates horizontally polarized photons here, and what we do is that we image this generation plane of this PPKTP onto a wedge mirror. Now, instead of splitting into based on momentum, as I have shown before, it can split according to the position. That means x1, all the photon pairs generated at x1 position will be reflected upwards, and all the photon pairs that is generated at x2 will be reflected downwards. And this is superposed, and one of this is flipped to vertical. So this is horizontal and this is vertical because there is a halfway plate. This halfway plate does not do anything, and this halfway plate flips the polarization state to vertical. And you combine this using a polarizing beam splitter, and you couple into a single mode fiber to remove any kind of position information later on. And this is we use a non-degenerate spontaneous parametric down conversion, and this is the polarization curves, and this has a brightness of 250,000 per second per milliwatt pairs. It has a fidelity, really great fidelity of 0.997. The only issue is the stability because it's a interferometer. So it's a Michelson interferometer, and these two path lengths has to be stabilized over a long time, over the period of the measurements at least. So in this case, what we have done is that we have used this piezo mirror to adjust such that, okay, along with this I have not shown that, along with this signal, the pump is also going a interference here, and we measure the pump interference fringes here, and based on that, we lock this interferometer into a constant phase. That's how we do these measurements. So at every point, you have to lock this interferometer. So this is for a in principle demonstration of this concept, but we need to have a better stability and more compact source if you want to use it for a field deployment applications. So this one, we have used a different approach. Instead of making a image of this crystal onto a wedge mirror, we go really close. We make we have designed a special half-wave plate. It's basically two half-wave plate. One is with 45-degree polarization angle, another does not do anything. So in this case, it flips the polarization and it does not do anything. And it combines using a BBO crystal later. So and then it is coupled into a WDM. So this is coupled into a WDM, and it splits into signal and idler using this WDM. And this is really compact. We can really go to like a laser pointer sized entangled photon source using this design. And you can see that this is the density matrix reconstructed using quantum state tomography. It has a brightness which bit less because we have used a collimated pump, and the fidelity is comparable again, 0.99 fidelity. It's close to 1. And only one problem here is that you have to have this special half-wave plate made such that there is no scattering at the middle. So if you use a Gaussian beam, it coincides with the center of this special half-wave plate. And if you have a scattering, it will scatter a lot of light and it will reduce your efficiency of collection. So because of that, we lose a little bit of efficiency. But if you can make this scattering less by polishing the surface, we can get much higher brightness and efficiency. Okay, so this is the last source, and maybe some comparisons in numbers. So if you consider brightness, this is kilocounts per pairs per second per milliwatt. This is of course because of BBO based one. It has lesser nonlinearity. It has 65,000. This has 1.2 million counts per second per milliwatt. Again, these numbers are based on silicon detectors. As these detectors has 50% detection efficiencies. So if you use better detectors, this number will go up. And this is with a narrowband laser, and this is with a broadband laser. And now the third one is the position correlation based one, and the fidelity is all comparable. The broadband is a bit less, but again it is sufficient to have any quantum communication application. And the heralding efficiency is also the lower fidelity is because of the tolerance of making your YBO4, the crystals. It has to be made such a way that the length should be exactly matching with your calculations, but because of the manufacturer tolerance, it's a bit difficult to get such high precision manufacturing. The heralding efficiency is again depends upon the detectors. It's similar in all the cases. This is less because of the scattering in the intersection. Okay, that's the source parameters. And the last, I want to mention some applications. So if you use a deep space quantum communication, the parallel path design has the brightest source, and it has a one of the best fidelity, and this can be used for deep space quantum communication. Even satellite based quantum communication, you can use this. All of this can be used, but if you want to use a if you want to deploy from a geostationary, then you need really high number of photons per milliwatt, then you actually this kind of source will come in hand. Now all of them can be compact. This can be extra compact. So the source without temperature control means in the BBO case, you don't need to control the temperature of the crystal. In all other case, you have to control the temperature of the crystal. And one extra thing is that generation of entanglement in other systems, for example, atomic vapor. So using this position-based entanglement generation, you can apply this into atomic vapor or even quantum dots. Because using that, you can have really narrow line with entangled photon source. So this is actually generic and can be applied in different source designs. As I said, if you have a heralded single photon source, and if you have not destroyed the position correlation, I can convert that into a polarization entangled photon source. And thank you. And this is our team. This is our group leader, Alex, and this is our colleagues. Thanks. I'm open for questions.
Hi, Chitra. I've sent you a question via the chat.
Okay. Okay. The phase difference between pump and SPDC photons with compensation and without compensation plots are theoretical or experimental. Oh, they are theoretical. We verify that using polarization correlation. So if they are not true, we will not get good visibility for the polarization correlations. Okay, Jeremy asked questions. What would be the potential application of such compact source in third type? Okay, this actually, as I said, you can have really fiber in, fiber out type of designs, and this will be used in many different quantum quantum communication experiments. So what happens if you have a if you want to deploy these photons, you need to have a really small compact source, and it has to be stable, and that's how it's much more practical to use this kind of design. Type 2, the second type, also it's bright. It can also be used, but it has more components. Like it has 2 BBOs before and after, and a YBO4. But in the third type, you can actually make a really compact source. On the other hand, it can be applied to different systems, and that is you can use that for generating a narrow line with entangled photon source. Okay, Vardhan has asked, can you elaborate the physics of spatial walk-off? So spatial walk-off is inherent to the bifurcation crystals, where you have a ordinary and extraordinary axis for this bifurcation crystals. If you are in an extraordinary axis, it undergoes this spatial walk-off, and that so when designing this entangled photon source, we have to take care of this effect. Okay, if you have any further questions, I am happy to answer, or you can drop in an email at this, and if you are interested in our group activities, you can go through this website. Thank you for listening.
Thank you, Chitra.
Thank you.